Okay, for this particular section that we have in linear algebra, there are items we'll be looking into concerning row space and column space, as well as what will be referred to as rank. And we have just some of the definitions for what we have along with theorems in this particular section. And we have for definitions of row space and column space of a matrix. Okay, we have letting A be an m by n matrix. Okay, the row space of A is going to be the subspace of R of n spanned by the row vectors of A, whereas the column space of A is going to be the subspace of R of m spanned by the column vectors of A. And we'll be getting into some applications very shortly. And for what we have regarding row equivalent matrices having the same row space, if an m by n matrix A is row equivalent to an m by n matrix B, then the row space of A is equal to the row space of B. And for what is going to be regarded as the basis for the row space of a matrix, if a matrix A is row equivalent to matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. And regarding row and column spaces, okay, row and column spaces have equal dimensions, and so the row space and column space of an m by n matrix A will have the same dimension. And for what is regarded as the definition of the rank of a matrix, the dimension of the row or column space of a matrix A is the rank of A and is denoted by rank of A. And we have note that some texts distinguish between the row rank and the column rank of a matrix, but these ranks are equal. So the volume we are using will not distinguish between these items. Okay, so now looking at basis and rank, and we have, say we have A to be a 2 by 2 matrix. Okay, so we have a square matrix, and the top row we have with 1 and 4, and the bottom row we have with 1 and 3. And we're looking at finding a basis for the row space of this matrix and also finding out what the rank is going to be. So just displaying this matrix in row echelon form, not reduced row echelon form, but row echelon form. And we have in the process, so if I make the bottom one for what I have in the second row to be equal to 0, I can just take R1, the elements, and subtract from those from R2. So I have 1, 4, 0, negative 1, and then having the lower right element equal to 1. Okay, so I'm just going to take the opposite sign in the second row. So we come out to 1, 4, 0, 1. And so we have for the row echelon form of what we have in the case of what was given for matrix A, we can say that we have for B, we have 1, 4, 0, and 1. And so we have first vector will be in reference to the elements in the top row, and the second vector, which will be designated W2, will be in reference to the second row elements. So you have W1 is equal to 1 and 4, and W2 is equal to 0 and 1, and these will form a basis for the row space of A. And since we have the row echelon form to consist of two non-zero rows, okay, we have the rank of A is going to be at 2. Now another case, just changing up the dimensions. So if I have A to be another square matrix where we have in a 3 by 3 arrangement, and I'm looking at displaying what I have in row echelon form. Okay, so I got 1, 4, and 2, and the upper left-hand value we have at 1. Okay, so 1, 4, 2, the top row will be preserved, and I want, okay, the next row to have like a 0 followed by 1, and the last row to have a 0, 0, 1 setup. And looking at the operations, so if I subtract what is in the first row from the second row, and simultaneously twice the first row elements to what is in the third row, okay, so we have this arranged at 1, 4, 2, 0, negative 1, 5, 0, 8, 10, and I can change the negative 1 in the second row to positive 1 if I take the opposite sign of the second row, which is going to change over from 0, negative 1, 5 to 0, 1, negative 5. So I got 1 in the upper left-hand corner, then I have 0, 1, and I want the third row to consist of 0, 0, 1. So I can change this 8 to a 0 through the process of subtracting 8 times the second row from the last row. So this last row will change over to 0, 0, and 50, and the 50 can be changed over to 1 upon taking 1/50th or of the last row, or in essence dividing the last row by 50. So we'll have 142, 0, 1, negative 5, 0, 0, 1. And so for the row echelon form, we're going to have b is equal to 142, 0, 1, negative 5, 0, 0, and 1. And looking at it row by row, we have a first vector 142, second we have 0, 1, negative 5, and W3 we have 0, 0, and 1. So we have 3 non-zero vectors, and those items will form a basis for the row space of A. And since we have B to consist of 3 non-zero rows, we have that the rank of A is equal to 3. Now let's say that if I have a matrix, okay, that is not square, but we have a 3 by 4 arrangement. And for this matrix A, okay, so to get this in row echelon form, okay, we're going to have in this one, so we have 1 in the upper left hand corner, which I want. So the row echelon form will preserve the existence of 1427 in the top row, and I want the second row to have 0 and 1 at the forefront. Okay, so looking at the process, if I change the 1 in the second row to 0, so I can subtract the first row away from the second, and changing what I have in the third row, where the leading coefficient is going to be changed over from -2 to 0. I'm also going to add twice the second row to the last row. So I'm going to have this adjustment where the second row will consist of 0, -1, 5, and 2. Last row we will have 0, 8, 10, and 18. And for the second row, I want the -1 to be changed to a positive, so I can take the opposite sign of the second row. So this will lead to 0, 1, -5, -2, and just creating the backdrop to where I can work with the last row. And I want to change the 8 to a 0, so if I take 8 times the second row and deduct from the last row changes over to 0, 0, 50, and 34. And we have for 50, I want to change this to a 1. So I'm going to, in essence, divide this last row by 50. And in the arrangement, we will have 0, 0, 1, 17 25ths. And for the row echelon form, matrix B. Okay, so it come out to 142, 27, 0, 1, -5, -2. And finally, I have 0, 0, 1, and 17 25ths. And we have, going row by row, we have the formation of these 3 vectors, all of which will form a basis for the row space of the original matrix A. And since we have B to consist of 3 non-zero rows, it just so happens that the rank of matrix A is again going to be at 3. Now let's say that if we have A to be a square matrix where we have a 4 by 4 arrangement, and looking at what we have here. So if I go through the process of subtracting the first row from the second row, as well as adding twice the first row to the last row, and subtracting the first row from the last row, in this case the fourth row. So again, the first column will consist of 1, 0, 0, 0, and for what I have in the arrangement, so the upper left hand corner value we have at 1, and the next row I want to start out with 0 and 1, but here I have 0, -1. So I'm going to take the opposite sign of the second row. So I have changing over to 0, 1, -5, -2. And getting closer now to the row echelon form. So I got 1, 0, 1. Then I want 0, 0, 1. And again, making this 8 in the third row to 0, I'm going to subtract 8 times the second row from the third row. And going ahead and making the -3 in the last row to a 0, I'm going to add 3 times the second row to the last row. So the third and last rows have 0, 0, 50, and 34, and 0, 0, -16, and -12. And again, changing the 50 that we have here to a 1. So I'm going to be taking 1/50th of the third row. So this will come out to 0, 0, 1, 17 25ths. And for what I have in the last row, I want to make the negative 16 to 0. So if I add 16 times the third row to the last, okay, we want to have the change up to 0, 0, 0, negative 28 25ths. And then changing that negative number to a positive 1, I'll be taking negative 25 28ths of the last row, so it'll come out to 0, 0, 0, and 1. So for the row echelon form, okay, we're going to have 1, 4, 2, 7, 0, 1, negative 5, negative 2, 0, 0, 1, 17 25ths, and we have 0, 0, 0, and 1. So we have all 4 rows to be non-zero, and so we had these 4 vectors, all of which will form a basis for the row space of A. And again, since B has 4 non-zero rows, the rank of A is going to be at 4. And if we look at changing the dimensions, okay, going from a square matrix in a 4x4 to one that is not square, where we're going to have a 5x4 arrangement. And you're going to have, in comparison to the previous example, this last row is just going to be the duplication of the 4th row. Okay, and so just kind of going through the operation that we have here. Okay, so we have ultimately what happens is that running it through the processes, very much like what was in the 4th case, but you're also involving the last row, which what we did with the 4th row earlier, where the 4th row is the last row, I'm just going to duplicate the process more or less in the last row. And the only additional step this time is that after all is said and done, like you have like a duplication of the prior example, but with this last row with 0, 0, 0, negative 28 25ths. And if I add 28 25ths of R4 to this last row, I have zeros running across. So here we have a 0 row. And for the what we have for the row echelon form in B, okay, if you notice, okay, we have the last row is going to be 0, but the 4 rows above will be non-zero. And so we have, so we're going to have, with the first 4 rows, we have these 4 non-zero vectors, and they will form a basis for the row space of A. And since B has 4 non-zero rows, the rank of A is going to be at 4. Okay, now for what we have regarding column space, and it says to find a basis for the column space of the following and to also find the rank. Okay, now what we're going to do here, instead of going through all the steps, and I'm kind of going through the same 5 matrices, but looking for the column space and finding the rank, which will be, at least with the rank, you're going to have history to repeat itself. So again, we start out with A with the same 2x2 matrix, but an approach to finding the column space is to take the transverse of A and put in reduced echelon form, or row echelon form, I should say. And so for the transverse, okay, you have the first row becomes the first column, first row, second column, and vice versa. So the transverse, you have 1, 1, 4, 3, and the row echelon form comes out to 1 and 1 at the top, 0, 1 at the bottom. And we have these 2 vectors, both of which are non-zero. And since the transverse has 2 non-zero rows, okay, we have, along with these row vectors forming a basis for the column space of A. It just so happens that since the transverse has 2 non-zero rows, we're going to have the A itself is going to have 2 non-zero columns, and we have that the rank of A is going to end up at 2. And going with our second example again, we have the same square 3x3 matrix, and if I take the transverse and display the row echelon form, okay, so we are going to have 1, 1, negative 2, 0, 1, negative 8, 0, 0, 1. All 3 rows are non-zero, and these 3 vectors spun off will form a basis for the column space of A. And since the transverse of A has 3 non-zero rows, A itself is going to have 3 non-zero columns, and once again, the rank of A is going to be at 3. And we have with our 3x4 matrix, okay, we have 1, 4, 2, 7, 1, 3, 7, 9, negative 2, 0, 6, and 4. But if I take the transverse, now the dimensions are going to change, okay, where we shift from a 3x4 to a 4x3. And looking at the row echelon form. Okay, so we have 1, 1, negative 2, 0, 1, negative 8, 0, 0, 1. Notice we have a diagonal array of ones, and we have with the last row, okay, to follow through with the row echelon form, okay, we have zeros exclusively. And so the first three rows will be the only non-zero rows, and we have the non-zero vectors W1, W2, W3 corresponding to the first, second, and third rows respectively. Those will form a basis for the column space of A. And since the transverse has three non-zero rows, A itself is going to have three non-zero columns. Once again, the rank of this matrix is going to be at 3. And going back to our square matrix earlier, now again, looking at what we have transitioning from the basis for the row space to finding a basis for the column space of this given matrix. If I take the transverse, okay, and do the row echelon form arrangement, okay, so the top row we have 1, 1, negative 2, 1, followed by 0, 1, negative 8, 3, and then we have 0, 0, 1, negative 8, 25ths, and we have 0, 0, 0, and 1. So all four rows will be non-zero, and the respective vectors, W1, W2, W3, and W4, corresponding to what we have in the arrangement, those will form a basis for the column space of A. And since the transverse has four non-zero rows, again, A is going to have four non-zero columns, and once again, the rank of this matrix, okay, for this reason, is also, once again, at 4. And we have with the matrix A in the prior case, when we looked at row space, okay, we had, again, the presentation of a 5x4 matrix. And looking at the basis for column space, if I go through the pathway of taking the transverse, so I'm arranging a 4x5 matrix and putting in row echelon form. So we have 1, 1, negative 2, 1, 1, followed by 0, 1, negative 8, 3, and 3. And then I have 1, 0, 0, 0, 1, negative 8 25ths, negative 8 25ths, and then I have 0, 0, 0, 1, and 1. And all of these rows will be non-zero. And the corresponding vectors from W of 1 all the way out to W of 4, once again, will form a basis for the column space of A. And since the transverse of A has four non-zero rows, A is going to have four non-zero columns. And once again, the rank of this matrix is going to be at 4.